Time.
Go for it.
So welcome back, everybody. This is lecture 6 of 6S083 18 S190. So after today's lecture, we'll be halfway through the course. There are 6 lectures left after this one, because Monday, the coming Monday, 20th of April, is a vacation. Well, what do you call it?
The holiday. It's
Patriots Day. So
normally there would be a Boston Marathon run on that day, but obviously not this year.
Right. So there's no class on Monday, and Tuesday is a normal Tuesday, so there's also no class on Tuesday. So the next class after today will be a week from today, on Wednesday next week, 22nd of April. So problem set 2 was due yesterday, and I hope you had fun with it and were able to get it to work. Can we have a show of hands if people liked problem set 2? So raise your hand if you liked it, or enjoyed it, or learned something, or, great. And raise your hand if you didn't like it. Hopefully no hands go up, but if you didn't like it, please feel free to raise your hand. Okay, well, that seems good news. No hands that I can see. Okay, great. So problem set 3 was released last night. So finally, in problem set 3, we're going to simulate an epidemic, an actual epidemic. So we're going to think about a population of individuals, people living in a school or a university where they all mix up all the time. They're always running around, campus, interacting with each other, touching surfaces. And so anybody can infect anybody else. And so they're just all mixed up, all in one sort of confined place. And so because of that, we don't really have to keep track. Oh, what did you lose my? Okay, can you see the slide?
Now we do.
Okay. So yeah, so everybody is mixing up. So it's what we call a well-mixed population. And so we don't need to keep track of exactly where each individual is. It doesn't matter where they are, because they're sort of always moving around and touching each other, or interacting with each other in some way, sneezing over each other, let's say. And so so we don't have to keep track of the space. And so in problem set 3, we won't have this idea of where the individuals are located. In problem set 4, we'll do a similar model, but now we'll keep track of exactly where they are in space. That's a bit more complicated, so we'll leave it for the next time. But you will be able to see in problem set 3, you should see when you run your simulation, hopefully, there's steps. I've tried to make it very clear exactly how to set up the simulation, what you need to define, how you need to run it, what the parameters are, etc. So hopefully it shouldn't be too much work. And you should see that it's reasonably easy once we've set up all of this, like these ideas about how to use Julia, how to do loops, how to store information in vectors, how to plot, that you can actually get a pretty nice simulation, visualization of the progress of an epidemic. And so you should see an actual, in the last problem of the last problem in last exercise in the problem set, you should see an epidemic outbreak. So you should see the number of infectious people sort of take off, initially looking like an exponential, and then hit a peak and then come back down when they recover from the disease. And so you should see figures that look like all of these figures that you've been seeing all over the place on the internet. So of course, this is still the simplest. So we're basically, this problem set is about getting the simplest possible model we can for that, but where we really do keep track of exactly what state each individual is in. So we really have individuals in this model. It's an individual-based model or an agent-based model, where we have, people who are interacting with other individual people and transmitting the infection with a certain probability, and then recovering with a certain probability. And that is enough to give you this effect of this epidemic outbreak. And because it's a probabilistic model, when every time you, or stochastic model, every time you run it, you'll get a different exact dynamics, right? So it'll either take longer to take off this epidemic, or it won't, or it'll happen more quickly. It might reach a higher peak or a lower peak, etc. And so you can actually, see this variability in the data, and then you can do statistics on that variability, just like we did last time in class. And as I say, in the next problem set after that, we'll actually add this element of that people are localized in space. And then, later in the course, we'll discuss, okay, what happens if people only interact with a certain subset of other people in the population? In other words, their friends, basically, or people at work. How can we represent that? How can we model that? And so we're sort of building up, a set of tools that you can then really, well, in principle, enable you to sort of define a really pretty complicated model and run it. And that's very similar to the things that people are doing, with the sort of real models trying to predict the outcome of this disease. Of course, there you need to include a lot more information and a lot more complication in the structure of the model, but the basic ideas are the ones that we're seeing in this course, and you just sort of need to extend them, have more different types of individuals, so in the model we're doing in the problem set, you'll just have S, I, and R, susceptible, infectious, and recovered states. In more complicated models, you might have also an E state, which is this exposed. So people who are not yet infectious, but have already been exposed to the disease, have already got it themselves. And then in more complicated models, you also add the fact that different people have different ages, different genders, different socioeconomic backgrounds, different propensities to the disease. And so you can add sort of more and more classes, and you have to define how those people interact. So some people, transmit the disease because they interact at work, other people at school, etc. So people are doing all of these complicated models, but you have to have lots of data to inform how those models are created. And so we're not going to, go there, but you should now, after this course, be able to go and look at those, research papers and actually follow what they're doing and be able to reproduce it, hopefully, if they actually publish their source code, of course, which almost nobody does, which is terrible. Okay, so after all of that, let's get on. So today, last time, so this is the title of the lecture. So what did we do last time? So we spent most of the lecture talking about how we can characterize a probability distribution. So we had, something that looked like this, again, so which was, a number, so it doesn't go below 0. The number of individuals, sorry, the distance, the total displacement of a random walker, say, and the probability that you have that displacement. And so we have this discrete data, and we were trying to characterize this distribution, and we did that by calculating the mean of it, and then calculating the width of it. And we saw two different ways to calculate the width, and the standard one is this standard deviation, which is the square root of the distance, the sort of average distance from the mean. So the average of your random variable's value from its mean, which we can write as the mean of x. So we've got these sort of two layers of triangular brackets. Let's just move this over a bit. So we've got these two layers of triangular brackets, and which mean the triangular brackets represent the mean. And so I need to take this distance from the mean, I square it, and then I average that distance, and I take the square. And that average of the square distance from the mean is the variance, and because that has units of sort of length squared, I take the square root to get this width of the distribution. So this is the mean, which is this average value of x. Another notation would be the expected value of the random variable x, which we write like that. This is an E in this sort of mathematical bold font with this two double, that wasn't very good. There's two bars on the left side of the E. The expected value of this random variable. It's another word for it. So this is more of a, this E notation is more of a sort of mathematician's notation, and this triangle bracket is more of a sort of used in, let's say, physics or engineering maybe. Okay. And then at the end of the lecture, we started talking about how to write generic code. So we saw that if we had two different types of random walker, a discrete one and a continuous one, what we did was we decided that we could write a jump function for each of them. So we had, you know, continuous jump with one function. When I call it, it gives me, it returns the size of a jump for a continuous random walker, and another function, discrete jump, which returns the size of a jump for a discrete random walker. And we saw that we could write a function walk, you know, which takes n, but it also takes another parameter, which is the actual jump function. And we can just pass in the name of a function, just writing the name down, no quotes, nothing weird, just write the name, pass it into the function, and that will run that function. When you call jump inside that function walk, it's actually calling whichever function you passed in as an argument to that function. So that enables us to write one version. So what does generic mean in this sense? It means we write one version of the function, just one set of code. But that code will run different, you know, will actually do different things depending on what kind of other function I pass into it. And so it will, what you'll end up doing is actually compiling two different versions of this function and calling the right one, depending on whether you're passing in this continuous jump or discrete jump. So you're effectively getting two copies of the code, but you're only writing one copy of it. And so, you know, because if we were to write two copies, one of them where we called the continuous jump function and one where we called the discrete jump function, that would be a total waste of our time, because everything would be the same except there's one line where we called this jump function. So instead of that, we abstract, you know, away, and we make sort of one generic function where which does both things, and we'll create, you know, let the computer do the code duplication for us, basically. Okay. So what are we going to do today? So last time right at the end, we started talking about how to define new types in Julia. So we'll spend most of today's lecture discussing that, because it's really a key way of getting abstraction in the modeling process. And well, yeah, so we're talking about modeling the real world. So if we want to, you know, or some aspect of the real world, if we want to model the real world, we want to represent the real world inside our computer. And defining a new type is a very good way of being able to sort of capture some features of some concept in the real world. So a new type, sort of, a type corresponds to a concept in the thing that we're modeling, in the sort of object of the modeling. Object of the model. And so then we'll look at abstract types, which enable us to, which just help us to sort of organize the types that we have, and as again a way of organizing our ideas about how the computer model represents the real world. And we'll talk again about generic code. And then, okay, so yeah, so let's just record what we were doing. We had these different types of walkers. You know, one of them had uniform steps, which were some real number in this interval minus 0.5 to 5. So we generated them with, I wrote it there, with rand. It's rand just generates a random number in the interval 0 to 1. And so rand minus 0.5 actually generates a uniform random number in the interval minus 0.5 to 0.5. And then, so what we did was made these two functions, discrete jump and continuous jump, as I was saying. And so now somehow the random walker is being, the type of the random walker is sort of encoded in which function we're going to use for that random walker. But it's still, but there's, and so then we had this function that we did define last time where we passed in this jump function. So here's what the function looked like. Here's where we call the jump function. And so now which function is actually going to be called, it just depends on which function we're passing in as an argument. And all of the rest of the code is the same, as I was saying. Okay, and we saw last time that there's this sort of stumbling block or difficulty that, well, we had to initialize this value of x in some initial position. We chose this integer value 0, whereas for a continuous random walker, we actually want a floating point value 0.0. So, so the code works, but there's just this sort of, the code works even if you pass in a continuous jump, and then this x, which started off as an integer, will sort of switch to being a floating point number. But that's somehow feels unsatisfactory and could lead to, used to lead in Julia to very slow code when you did that. It doesn't anymore. That's been fixed, but still it's unsatisfactory and there's something wrong, right? So somehow, as I was saying, the information, basically you need two pieces of information. You need the fact that you have an integer 0, let's say you need an integer and the discrete jump function, or you need a float, you need this pair of information, or you need a float 64 and n64, let's say, and float 64 and the continuous jump function. You need a pair of information to really do this in a satisfactory way, and then you want this x. Here, you want that initialization to be, the 0 value of whichever of these two types is sort of the one that you're interested in using. And so basically, whenever we have, more than one piece of information about an object, we should actually really think about putting those pieces of information together into a package. And that package is a type, a composite type. So, composite meaning it's made up of pieces, several pieces, and you're composing them, you're putting them together into a box, right? So, container, let's say. So, yeah. So, I drew this picture last time, so I'm thinking of, we're going to define a type called a, discrete walker. This is sort of the shape of, and it has two pieces of information. Let's say, this is not exactly how we're going to code it, but it has this type, it has the information that it needs an integer value, and then it has, in some sense, then we want this jump function as well. So in other languages, you would put the jump function actually inside, right? The way I just presented it, it looks like, oh, discrete jump should actually belong to this discrete walker object. And so the natural place to put it is inside, you might think. So that is the standard object-oriented paradigm. So maybe I should actually, just draw that over here. So we're going to have sort of a standard object-oriented paradigm. So that's like, C++, Python would be what I just wrote. So you would have sort of, what is a discrete walker? It's going to have a position x, which is of type integer, which I'll write in the Julia syntax, : integer, : n64. And then we'll have a jump function as well. So I used to like visualizing this as sort of, I have a lever on this box, right? So for example, I have a lever, and then over here I have a light bulb. And so I can pull on the lever to say jump, and the light bulb will tell me, tells me the position. And so those functions jump, and let's say there's a function called pos that's going to report the position that it's in. Those functions were actually somehow belonging inside the object. So that's the standard paradigm. And now what happens in Julia? So the only thing that lives inside this object is the data. So I have some data x, which is of type N64. I always draw this box too small. So this squiggly line is just supposed to represent some piece of memory, right? Some space in memory. And then I'm just giving it a label called X, a name called X, and remember that the type is telling me how that piece of memory behaves. So it's behaving as if it were N64. That's the only thing that lives inside this discrete Walker template. And then we have a jump function that lives outside somewhere. And so we have a jump function that knows how to act on an object of this type. And then if we had it over here, over here we would have also a continuous Walker type in C++, and we would have its x, which was a float 64 type, and then we would have an its jump function defined inside, right? In Julia, we have only the x, which is of type float 64. And then we have a jump function with the same name. It's the same function, but we have two different methods for the function. So two methods. So we have one jump function that acts on an discrete random walker and one jump function that acts on a continuous random walker, but the jump function does not live inside the object. Does not live inside. So in some sense, you could say that in other languages, the noun is more important. So the object, the thing, the discrete walker or the continuous walker is sort of primary. And in Julia, the verb is primary. The things I can do to the objects are primary. Verb is primary.
I would have said that in Julia, it's symmetric.
Yeah.
In the verbs.
Yeah, okay, sure.
While in object-oriented, it's primary, and there are other languages which I would have thought of.
That's probably true. Yeah, thanks. Okay, so that's a lot of philosophy. Let's get to some actual stuff. So I think I'm just going to jump straight to the notebook, and we'll go over again what I started last time. How do I do that? Share. Okay, can you see the notebook?
Yep, looks good.
Great. So, defining new types in Julia. So, so last time I started by using a struct. So let's call it my discrete walker, but I'm just going to jump straight to using a mutable struct. And so it's going to have inside an N64 and it has inside one variable x, which is of type N64, end. So this is this is the way I represent in Julia this box that I had, which had one piece of information in. If you want more information than that, so something else, let's call it, this is a something else type. So types in Julia, by the way, types have in capital letters for each word in the type name. Camel case. So yeah, I'll just put capital letters for each word in the type name camel case. Okay, so something else is another type. So it could have an X, which was of type N64, and it could have a Y, which is of type float64, and it could have an S, which is it could have a name, which is a string. And it could have a vector, and it could have any kind of thing inside. It could even have a MyDiscrete Walker inside, and that's what it would look like. So you just list these variables one after another, and usually you want to give them, you want to tell it what type they have to be. It is possible to not tell Julia what the type is, and then you can store anything in that position, but that's going to be slow. So usually you don't want to do that, but there are some cases where you might want to for some reason. So yeah, so if you have questions, do feel free to, as usual, write in the chat, and somebody will answer or will raise the question and I'll answer it live. So I'm not monitoring the chat, so if somebody wants to tell me what's going on, if there's something I should talk about, please do. Okay, so so that was just an example of how to define a type with several things inside, right? Several fields. So these are called fields. So you just list them one after the other with just blank lines, not even blank lines, just one on each line. And you need this end at the end. Sorry. So I probably should not have made it mutable just so we can see the difference. So what is this? So okay, so if I just type, so if I run this cell, that defines a type, right? So MyDiscrete Walker now exists. The name MyDiscrete Walker now exists, and it refers to this type, right? Refers to the type. So I can talk about, so it's not actually that useful, but one of the things you can do with that is just say methods of it. So let's do methods of it. So if you remember, I think we've been over this, methods tells me which versions of a function I can run, right? Which methods or versions of a function exist. And so what we see is that Julia automatically, when I created the type, right, so Julia automatically created two what are called constructor functions. Constructors, which are functions to build objects of that type, to create objects of that type. It automatically created those when I defined this type, MyDiscrete Walker. And so one of them takes an X, which is of type N64, because that's the type of the thing that I put inside MyDiscrete Walker. That's a function that takes in an N64, right? So MyDiscrete Walker, and I pass in 3 as if it were a function. Actually, that it created a function with this name, right? So in some sense, you can think of this name as referring to sort of 2 different things. It refers to the type name, and it refers to a function with that same name that creates objects of that type. So if I do this and I call it W, then what is that? So now W is an object of that type, right? So if I do type of W, it will tell me, oh, W has type MyDiscrete Walker. So I just created a new type that's basically equivalent, to a real, let's say a float 64 or a complex number or a vector in Julia. So the type that I just created is on the same sort of level. It's just as good as the types that already exist in Julia. They were just defined in this sort of similar way or the same way in Julia source code somewhere, right? So let's look at that. So like you can make a complex number in Julia by calling this complex 3, 4. It's the same as if you just write literally 3 plus 4 im. Im is the imaginary part, right? Im is like I in mathematics. So the square root of -1. So you just write that as im in Julia so that they don't take away the possibility for you to use the variable I in your own code. And so so this is just another way of creating that number by calling this constructor function complex. So if I do @edit, or let's say which complex 3, 4, it tells me where this thing is defined. It's in line 12 in the complex.jl source file. If I click on that, it'll take me to that line in the Julia source code. And you can see that they are defining a struct called complex, which contains two things, a real part and an imaginary part. And I'll come back to this T later. But that is exactly how a complex number is defined in Julia. It's just has two things inside, just the way we're doing it right now. Okay. So what I'm saying is, when I define a type in this way, it's just as good as the complex type that came predefined with Julia, it just happened to become predefined. In many other languages, the types that are sort of built into the language are special. In Julia, that's not the case. Your own user-defined types are just as good as everybody else's types. In particular, they can be just as performant or just as fast. You're not going to have a penalty for writing your own types, which is different from most languages. Okay, so I have this W. Another way of asking is W. So if I were talking about sort of the world, I could say, is W a particle? Is W a molecule? Is W a thing that's doing a random walk? And in Julia, I can ask that as well. So I can write W is a my discrete walker, and it will tell me that it is. And so, that means that W is what we call an instance of the type my discrete walker. Or it's an object of that type. So that's just another way of saying, of comparing the type of W to the answer, my discrete walker. Okay, but there's this other function, right? When we did methods of my discrete walker, there were two functions. So what is the other one, do you think? What is the other one doing? So it's saying I can pass in an X, and it's not restricting the type, right? So reminder, this notation means that this is a type annotation. That means this version of the function only works on and when it receives an X, which is of type in64. So let me write that down. So my discrete walker X in 64 is a method that works only when it receives an argument X of type in 64. Right, so when I call my discrete walker with 3, it will call that constructor. And all that constructor does is fill in this value inside here and create an object. So reserve memory in the, reserve some amount of memory where an object of this type will exactly fit. And that amount of memory is exactly going to be big enough to store this 1 in 64 in this case. Or in this case, it'll be big enough to store these three things. And then we have to be worried about how string gets represented, and we're not going to worry about that right now. Okay, so what about my discrete walker of X? Well, that has no type annotation, no restriction. So that will work for an X of any type. Will accept an X of any type. So there is actually a type called any in Julia, which represents literally any type. So, a string, yeah, okay. So I can, for example, try to call it with 3.0. What do you think will happen? So 3.0 is not an integer, right? 3.0, is that an int64? No, it's not. Because the 0.0 makes it into a float. Sorry, type of 3.0 is float 64. It is not an integer. And yet, this is the number 3, right? It's the sort of the same in mathematical terms. It's equal to 3. So maybe it should work. So let's see. Do you think it should work? My discrete walker of 3.0. And the answer is, okay, it does work. So what it does is automatically, so this other function that it defined automatically takes this value that you pass in and it tries to convert it into the type that it knows has to go inside the my discrete walker. Right, so in this case, it's managing to convert 3.0 into 3. Okay, but what happens if I do 3.1 instead? What do you think happens? So, we could guess, or we could just ask Julia, right? So often the answer to, well, what does Julia do in such and such a circumstance is just, well, just ask Julia, what do you do, right? So in this case, it's going to actually give me an error. And this is an error that you might see, like, hopefully not too frequently, but now and again, called inexact error. What does that mean? It means that it's trying to, as you can see here, what is this? This is actually a conversion call. It's trying to convert 3.1 into this type, right? So if I do int64, that's the way, or one of the ways you can convert from one type to another, if the conversion is possible. So in this case, it knows that yes, I can sort of, so in other languages, this would be called typecasting. I can you know, turn this 3.0 into an int64 and I get an integer response, an integer output. But in the case of int64 of 3.1, you cannot make 3.1 into an integer, right? You can truncate it to an integer, but that is changing the 3.1. And so it won't let you do that automatically. You actually have to tell it to do that. And of course you can, there is a function to do that in Julia, trunc to an integer of an N64 of 3.1. Truncate to an integer, and then it's fine and it's happy. Or you can use floor. You had to use floor in the homework and people were struggling with floor, sorry about that. But floor finds the closest integer underneath 3.1. But if you just call floor with 3.1, it will still do that. It'll calculate the closest integer that is below 3.1, but it will return a floating point number, right? So sometimes we actually want an integer and then you have to explicitly tell it, oh, make that an integer, please. Or of course you can do int 64 of floor of 3.1. So again, int64 is the name of a type. And what we're doing there is, you know, basically you can think of it as constructing an object of type int64. So it's a function with the same name. So it's a constructor. But what that constructor actually does is tries to convert that number into that type. Okay. So these are a lot of, you know, fiddly details, but I think it's important to sort of understand the context. Okay, so that's what the other this other constructor was doing. Great. So we have, you know, if we do this, w equals my discrete walker of 3, then I can really say I have an object w in my world inside the computer, in my mini world, that is a discrete walker. Right? I can really say that now. So that is the point of types. And, you know, normally you wouldn't just have one thing in there. I mean, you can only just have one field, but for example, in the homework and problem set 3, you're going to have an agent that has, so, you know, let's just let's just go over that. So in the problem set 3, you're going to have a mutable struct. Well, let's actually load it up. So yeah, in question 2, exercise 2, you're going to have this mutable agent that's defined like this. Well, I can just do it. Yeah, so you're going to have an infection status that in the problem set is going to be a special type called an enumerated type, so that you restrict the possible values that it can have. For now, we'll just call it an integer. I go into the details of how to make it an enumerated type in the problem set. And so the status is an integer, so that's going to be, you know, 0 if you're susceptible, 1 if you're infected, 2 if you're recovered. And you're going to have num infected is another integer, which is going to tell you how many people this particular agent infected during the course of the infection. Right, so it's a perfect example of where you have more than one piece of information that sort of belong together. They belong to this particular person. They belong to this particular agent, and so they should be collected together into one thing, one group, one package, right? One packet. So we're collecting information. That's the point of types, right? In Julia, collecting information into one packet. Belongs together. So there's a word for this, which is encapsulation. Unfortunately, that word has been sort of misused or overused to mean encapsulating both data and code and functions together in traditional object-oriented programming languages. But I mean, already C in 1970 had struct, right? So this, or 1972 or something. The word struct, meaning structure, this is some structure that I'm defining. I'm defining the structure of a type as you're having this and this and this sort of packaged together in a box in some particular order. That's a structure. So already C had that and did not allow you to put functions inside the type either. And I don't know if they use the word encapsulation. Anyway, I like the word encapsulation, but I don't like the fact that it's sort of been extended to mean that you have to put the functions in there as well. Anyway, okay, good. So we're back to our discrete walker. And now we want to make this walker actually do something, right? That's the whole point. Otherwise, this is just data that's going to sit there and nothing's going to happen to it, and it's going to be very sad. So, by the way, it is actually more common in Julia, I would say, to use immutable structs. So here's an example, immutable struct. That's the name of the type. So let's say that has an integer. So we did this last time, and it has an x and a y, right? So you'll be using this in the next problem set. So not with that name. So then I can make a new object called z, which is of this type. And so what am I going to pass in to this constructor function? So let's have answers in the chat. How am I going to construct an object that is of this type?
By the way, Dave, whenever you're ready, we have another question.
Mm-hmm.
Should we go ahead? Okay, so so the question is, you can use convert to change types, or you can use the name of a type like you showed us.
Right. Yeah, you can write convert to type int64 the value 3.0 and it will work. You can use convert int64 and the value 3.1 and it will not work. Yeah.
Or you could, but you can also do it without the convert command.
Right. I can also use this other way of writing it. Yeah.
Are they exactly the same? Is there any benefit of one over the other?
So I was wondering that as I was saying it. I believe that it is defined such that when you just do this int64 of this value, it will call this convert function.
I was wondering that too. Yeah.
By default.
Is it if you do add
actually no? Or does somebody else know?
The panelists are also not 100% sure.
Okay.
That's what we're guessing, but we're not. If you go add which, will it tell us?
So I don't think it will, no.
Oh, okay.
Maybe it will.
Yes, it's all right.
So maybe I didn't actually say what at which does. So at which just tells me exactly which method am I calling, right? So if I do sort of methods of int64, it turns out that there are quite a few of them. You can int64ify can turn into an int64 a lot of different things, or try to. And so at which actually tells me which one of those am I calling when I pass in an object of this particular type. So in this case, it's the one that's int64 of an x, which is a float 64, and it tells me where that's defined. Let's click on there, and I'm just fearing that it's going to be some pretty incomprehensible piece of code. So it's not actually doing a straight convert now. It's doing something more complicated. Okay, but maybe convert does exactly that, or maybe it's the other way around. Maybe actually convert. When I call convert to int64, maybe it just calls the constructor instead. That would also be a possibility. So at which convert, yeah. So this is saying, so convert to a type T, which is a subtype of number. So we'll talk about subtypes later. Convert and some number to that. So where is that defined in some other file? And that is just construct that. Yes, it's just called the constructor. So the constructor is actually more fundamental, and convert is calling the constructor. That makes sense.
So they are exactly the same.
They are exactly the same in the case of numbers.
And Julia even lets you find
you can define, if you define your own type, you can define how to convert other things to it. By just defining a method of convert on your type. So maybe we should actually see that later. Okay. Okay, so let's carry on. So now we want to do something with my random walker, right? Do something, make the walker move. So, oh yeah, so what I wanted to say about immutables. Oh yeah, so I was in the middle of asking a question, which was, I have this example immutable type. How can I make an object of an example immutable type? It has two fields. So what do I need to do there? I actually need to pass in two arguments separated with a comma. And let's call that Z. And now Z.x is the first one that automatically got filled into 1. So it takes these numbers and puts them in order, one after the other. It makes sure that the types of those objects fit with the types that are allowed in this example immutable object type. And it puts those inside. But now, because it's immutable, if I try and modify any of those values, it actually gives me an error. So I did show this last time, but hopefully it's more clear now what's going on. So there are two different types of structs, two different types of these sort of ways of making an object. You can either say, I am allowed to modify the fields, in which case you have a mutable struct, the language, yeah. Or you can say, I am not allowed to modify them, in which case you have an immutable struct. And so it's actually more common in Julia to use immutable structs when you can. And that has to do with performance, because it turns out that Julia is pretty good at optimizing a lot. These immutable structs, they sort of can live, there are ways to, yeah, let's not go into the details. It's just better for performance if you can do that, usually. I believe that's true. Okay, so let's make a walker move. So again, I've written this so many times. So x equals, I've already forgotten the name of the type, my discrete walker. And as I said, you can use the tab key to complete just in one. I just type the tab once and it completes this name, right?
I think the tab thing is what is like the most useful thing that
right.
ever told me.
Yeah, the tab key is very useful. Yeah, exactly. Okay, so great. So before we actually move on to make it move, so I'm sorry, we're not going to make it move yet. Okay, before we make it move, so it's a bit annoying that I have to pass in this number, right? Because, suppose I want to make 100 of these things, and suppose I want them all to start at 0, well, I would have to call explicitly my discrete walker at 0 every time. Or, maybe that's not so onerous because there's only one value here. But if there were more values that I had to stick inside my object, then that would be pretty annoying. So, yeah. So I want to define what it means to call my discrete walker with no arguments and have that automatically put 0 in if I choose not to put 0, right? And so if I try and call that, what happens? Well, it gives me an error. It tells me there is no method matching it, right? None of the versions of the function, my discrete walker, the constructor that we have so far, allow me to not put any arguments in. Let's just remember what they look like. They all take at least one argument, right? So how can I fix that situation? So I'm actually going to define a new method. So how can I define that? So I want to define this. So in Julia, because it's going to be a short definition, I can just put that on the same line. So I have to put the parentheses. This is actually defining a function. You can see it changed color. It was black, and now when I put the parentheses, it changes to green, and then when I put the equals, it changes to blue. And because it knows it's defining and it's actually telling me this is defining a new function in line. And what is that going to do? Well, it's just going to call my discrete walker and put the 0 in there, right? So it's actually going to create an object of type my discrete walker and return that. So now, if I do methods of my discrete walker, now I see that I added a new method, right? That was the point of doing this, was to, sorry, I'm having issues with my technical issues. Yeah, it added a new method. There is now this version of my discrete walker which takes no arguments because I just created it, right? So this is called it's a type of constructor, and it lives outside the definition of the type, so it's called an outer constructor. So it lives outside the definition of the type. You can actually make functions that live inside the definition of the type. They are called inner constructors, and they exist so that you can force some condition every time you create an object of a certain type. You can actually intervene in when the object is constructed so that you can only allow certain ways of constructing the object. But usually we don't need to do that. We don't need to mess with that, at least in my experience. It's more annoying to do that. It's much nicer if you can just add new variants of this thing, but then it's harder to enforce, enforce things. Okay. So, okay, great. So now I can just go ahead and create a walker by doing y equals my discrete walker, and that will make a version of this function, make a version of this object with the 0 automatically put inside. Okay. So that's something you're going to use at some point in the problem sets. Okay, so now we're going to make it move. Now make it move. And so we're going to define a jump function. I guess we did this last time. Yeah, I think so. We're going to define a jump function that works just for my discrete walker. And it's going to modify this object, right? That's why we made it a mutable struct. So if you don't make it a mutable struct, you could also do that, and then you would have to actually, so you can't then change its position, right? So then you would actually have to recreate each time a new object when you made it move. So you can do that, and I think it will still be efficient because the compiler is clever. But this is, yeah, so there's this tension between defining immutable objects, and then you have to reconstruct them, or defining mutable objects, and then it's not clear necessarily which is going to be more efficient or better code. So, yeah. Does anybody else want to say anything about that? That difference? Shashi, do you have anything to say? No. Okay. Maybe he's not listening. Okay. So, yeah. So let's, because it modifies, I'm going to put my exclamation mark as usual, and I'm going to define it. So just for clarity, we're going to do it in a long form function. What am I going to do? I'm going to take the position inside my walker, and I'm going to remember what it's called. I think I called it x, the position. And so I'm going to say that I'm going to modify it by adding rand of -1, 1, as we're used to, right? Or you could, set r equals rand. Yeah. So that's a good way of writing it. Okay. So by the way, another thing that would be nice is if you actually had, so we can actually write a position function, as I hinted. So just the position of w, which is of type my discrete walker, is going to be just return the value w.x, right? Because I immediately, just now, I just had a problem of remembering what the name was of this field inside W. So actually, by the way, if I put w.tab, just type w dot, and then I type tab, it will actually give me a list of all the fields inside. So for example, z.tab, z was my object of type example immutable, has 2 fields inside, and it's actually listing them for me. And you can get those like this as well, property names of W will give me a list of all of the names of the fields of W. It used to be called field names. I think does that still work? No. And field names only works on the type. Yeah, that's weird. Okay. Anyway, property names of W works. So yeah, so fields. Yeah, there's something called properties as well. Let's not go into that. Okay, so this colon is called a symbol. Colon x is a symbol. So what we're seeing here is a tuple. It's right, parentheses with commas means tuple or tuple, and colon x is a symbol, so a special type of string. Okay, good. And so property names of example immutable gives me just of z, sorry. property name of Z of the actual object itself gives me the list of fields that are inside that object that I can use. Okay, yeah, so I have this pos function. So if I do pos of W, now I have a much more memorable name for, you know, what's going on. And also that's advantageous because later on, I might have some other kind of walker whose position I also want to find, but maybe that walker does not use .x, right? Maybe it has a field called Y or a field called position. And so I want some interface. So this is like an interface to my object that sort of removes me from the internal details of the object. So I only have to define it once, you know, and then I now have a sort of user interface that the user should always be using the position of this object. And then, you know, even if I then change the internal representation of my object, for example, maybe I don't store the position anymore, I store a displacement from some origin instead, then I can still use this function to get the, so it's like a more abstract, you sort of again, you sort of removed yourself from the implementation details. And then I probably want a set position as well. Set position of W. So what is that going to do? That's going to modify W, and I need to tell it which position, which new position I want. And so in this particular case, what it's going to do is go inside and change the value inside W. And so if I do that, then I can rewrite my jump function. Although, you know, my jump function is kind of nice like that, I can actually rewrite it now. So sort of old position equals pos of W. And now I'm going to set the position to old position plus the jump function of W. No. Yes, the jump function of W, where jump, you know, tells me, oh, it's random -1 + 1. Right? So jump with no exclamation mark, with no bang, is returning just the step size. It's not modifying anything. It's just creating a step length. And then now I'm modifying my walker by saying, oh, get the old position, add jump of W to the old position, and now set the new position to that, right? And so you see that in this new version of jump, I never actually talk. So in this version of jump, I never refer to internal details, but to internal details of the object. And so I can rewrite, you know, if I rewrite the internal, how the internals work, or I use some other object with different internals, the same function will work as long as I define these interface functions pos and set pos. So these are called getters and setters sometimes. This is a setter function, and pos is a getter function. So my accent of English, I don't pronounce R's, the letter R, I don't pronounce, so getter function and setter function, right? It has a yeah, okay. So this is a pretty general way of defining jump on this random walker object. Okay, great. And so now we can write walk. So I'm going to take an object, a discrete random walker object. I'm going to take a number of steps, and we're just going to walk it. So we're going to make it jump, make that particular walker jump. So jump bang of W. So as I said last time, you can think of jump bang as being an order, right? An instruction. That's why, you know, if I read that out loud, it would be like jump, jump, please. And so it's an order, yeah, a vocative case. If you learn, you know, any languages like Latin or anything, that would be a, yeah, the sort of exhortation, an order that you're giving the particle. Please jump by, yeah, please jump 1 step, end. And that's all it does, right? And then probably we want to return the actual object as the result of this function. And so if I start off with my discrete walker at 0, I do a walk of size 10, then I need to tell it, sorry, need to walk my particular, so that gave me an error, right? Let's actually take a moment to look at that error. Method error. So whenever you see a method error, that means that it's trying to call a version, so the function walk, of course, exists, right? If I ask, does walk bang exist? Yes, it does. There's a function called that, but if I look at the method list of walk, then there's only this one function which has to take both these arguments. And so because I only gave it one argument, there is no method. It's true that there is no method of that function. The function exists, but there's no method matching walk bang of N64, right? So if the function doesn't exist, right? So let's say a weird function, I try and call that with 10, that gives me a different error. It just says a weird function is not defined, right? So this error is telling you, oh yeah, that function name does exist, but that function does not have a method, a version that only takes one thing of type N64, which is what this syntax means. Okay, so let's call it properly. So walk, I need to give it the walker and then 10, and then that makes W actually move, right? So W has been mutated, has been modified, or modified. So yeah, and that's why it has this bang, right? I'm mutating, I'm modifying what's inside the object, the values stored inside the object. Okay. So again, there's this tension between, do you want to have mutation or do you not want to have mutation? So that's an interesting discussion that we won't have right now. Great. So now we get to the continuous walker. So we're going to define a new mutable struct, which is called my continuous walker. So there's a reason I'm putting the my in there, because in a moment I'll take it out. My continuous walker, because remember that if you define a type in Julia, in the same session, you cannot redefine that type as something different because of technical reasons, at least at the moment, but probably never. And so you will have to, if you want to reuse the same type name, you'll have to restart. So a simple solution to that is just to sort of start adding 2, 3, 4 to the end of the type, and then there's a trick you can do to make it more usable, but anyway. Okay, so this is going to have a y, let's call it y this time, just to point out. Let's call it y, and that's going to be a float 64. And so now I need to go through, right? So I can do what w equals continuous walker, my continuous walker of 3. And now you see that it converted that 3 to a float 64 by the same mechanism that we were talking about before. So W is of a type my continuous walker. And now I want to make W walk, right? So let's try that. So jump of W, what's going to happen? Question, chat. What do you think will happen? Will it jump? Method error, yeah. So it knows that jump bang is a function, but there is no method where I pass into jump bang a continuous walker object. Why? Because I only defined it for a discrete object, right? And that makes sense because I don't want to use the same jump function for a continuous walker. So that was sensible. I restricted it to only working for a discrete walker. So I actually have to define my jump function for a continuous walker. So it's rand, right? So it's let's do jump without a bang. That gives me how much it's going to move by. So we were just using this rand n, which gives me a Gaussian distribution centered on 0 with variance 1, standard normal distribution, standard normal random variant. Sorry. Yeah. So now, okay, but I defined the jump bang function. I defined it. So now it should work, right? I defined it in terms of jump without the bang, but it doesn't. Because for the same reason, right? I never defined jump bang in general. I only define it for jump bang of my discrete walker. So let's go back and get that code for jump bang. So now if we look at jump bang, we see that actually, oh, well, this code should actually work for any random walker, right? As long as I define position and set position. So what we're going to do is take that code that we had before and just remove this W being of type my discrete walker. I'm just going to remove it. And so now it will take any object of type W. So that's a bad idea because, then it looks like I can pass in 1 to that object. And so now I'm getting a different error. I'm not getting a method error anymore for the jump function, right? It's telling me that the method error is not on the jump function. It's managing to call the jump function because the jump bang function takes anything now. This is of any type, right? Takes an argument W of any type. So in particular, I can pass in 1. Great. So let's pass in 1. What happens? The first thing it tries is old pos equals pos of 1. And if you see, it's telling me indeed, there is no method matching pos of 1, pos of an integer. And it tells me even where it is, right? So it's telling me that the stack trace is telling me that, it's in the jump bang function in 80, and this :2 means on line 2. And I can add line numbers by escape L, and then I see, oh yeah, line 2 is this line. So that is the problem. So it has gone into the jump bang function. So this is a bit unfortunate, right? We should not really allow the jump bang function to take arguments of type 1, of type integer, like 1. It should really only be working for random walkers, but it should work for any random walker. And at the moment, the only mechanism that we have to make it work on any random walker is to just remove this annotation completely. So in a minute, we'll see how to solve that problem. But let's just do this for now. So now this function jump bang of W should now work on my continuous walker, right? So W, I think, is now my continuous walker. Sorry, I should have given it a different name. So W is a continuous walker. So now we're going to jump bang of this W. So it will successfully call jump bang of W, but now it has the same issue, right? I have no function pos of my continuous walker defined. Why is that? Because I defined pos only for a discrete walker, right? But so now let's define it for a continuous walker as well. So if continuous walker had the same w.x, right, the same name of its position, then I could actually use the same function for both continuous and discrete walkers, but it doesn't. So I actually have to define it separately, and I'm going to say it's w.y, and the set pos of w, which is my continuous walker, is w is w.y equals whichever position I'm passing in. So yeah, so this gets confusing because I have 2 equals. You can write it like that, but it's less confusing if you just write it as a full function. Okay, so now that I've defined pos and set pos for my continuous walker, in this moment, without having to restart Julia or anything, I can now do jump bang of my continuous walker. No, I can't, because I wrote the code wrong. Sorry, I never actually ran the code. It's set pos bang of W, and I need to give it its, I need to put the W in the jump function, right? So set pos of W, and I need to give it the new position. Okay, and now it works. So this is really cool, right? So what happened? I passed into jump a new object, my continuous walker. It had never successfully completed this jump function before with this my continuous walker. And what it did was realize in that moment when I called the function, oh, I can just run through this entire function with this type my continuous walker. Pos works, set pos bang works, jump works, everything works. And so it will create in that moment a specialized version of this jump bang function that works specifically for my continuous walker. So it will actually compile a new version of the code for that particular type. And then every time I run it after that, it will call that particular version as long as I pass in a continuous walker. Okay, and then we have this walk bang function. So now I should be able to walk bang a walker with n steps, right? Even if it's my continuous walker. And the answer is no, because once again, I was silly. I restricted walk too much. So this is a common problem in Julia. You define, you write some code and the code does some particular algorithm or whatever, and you restrict the type because you're used to that from other languages or because it's natural. You restrict the type of thing that you can pass into the function. And then it turns out later that actually you can do something even more clever if you, for example, you have a function that calculates some quantity. So now suppose that you want to differentiate that function. It turns out that there's a clever method that we might see later in the course to do that, called automatic differentiation, where you pass in a different type that's designed to calculate the derivative automatically. But you have to pass in a different type. And so if you over-typed your function, if you restricted it in this way, then you will never be able to pass in this other object. And so you should actually try and restrict as little as possible the types of the functions that you have. So in particular, let's go back to this walk bang code. Maybe I should just rewrite it, it'll be faster. Again, we restricted walk bang to only take things of type my_discrete walker. So I can just, again, remove that completely. Just remove that type annotation. So this walk bang function will now accept any two arguments, but it will only work, of course, if I can actually call the jump bang function, right? So again, if I just do walk bang of 1 and 2, it'll give me an error because again, it's trying to, but now look where the error is. The error is in the pos function, right? Which is called inside this jump bang function. So again, it's going into this function, it's trying to run the code, it's trying to run each line until it fails. And when it fails, it'll tell you, where it failed and why it failed. And then you can start debugging and see, oh, maybe either you gave it, objects, you gave it arguments that were of the wrong type, or there's an actual bug in your code. Okay, but in this case, so now I have this walk function, and as soon as I define that walk function, because everything else works, now I can run it on my continuous walker, and it will return the continuous walker, right? And so W has done a random walk. And so this is what we mean by generic programming, generic code. So this code works for any object W that knows how to jump bang itself, right? How to jump. I think that is super cool. And that is, so this kind of process that we've gone through today, I know I've been laboring it a bit, but it's exactly the kind of thing that you do all the time in Julia. So you write these zillions of tiny little functions, right? Each of these functions seems so sort of pointless almost when you run it, but we're gradually building up piece upon piece, block upon block. These tiny little blocks that just do one piece. But by doing that, we're actually removing ourselves from the implementation details inside the object. And we're building up code that can run, in lots of different calculations with the same piece of code. Okay. And so, by the way, if you come from other languages, you might be worried, oh, function, when I define a function and then I call that function calls are slow. Function calls have a lot of overhead because what they have to do is sort of put everything on hold. And that means save a lot of variables in a stack and then sort of change to some other sort of context and maybe set up some new variables so that I can run this function and then undo all of that when I leave the function again. And it is true, function calls in Julia are also slow, except that these tiny little functions do not actually end up as function calls. What actually happens is that they are inlined. So what does that mean? It means that when I have my code for the jump function, right? Although it looks like I'm calling the function pos of W, because pos is a short function, it will actually insert, when it compiles the code, it will not compile it as a function call. It will just copy the code for the pos function right in here, in this version that it's compiling. And then, so you will no longer have this function call overhead. And it will do that for all of these small functions. And so you get, at the expense of having a bit of a longer piece of code, you will get them, it will be much faster. And of course, that's a problem. If the code gets too long because you inline too much, that will also cause slowdowns. But so there's some heuristics to balance these things out. But basically, it's very idiomatic, it's very common, it's the correct thing to do in Julia, to write all these tiny small functions, just build up piece by piece, make sure that each function works properly, right? And just to finish, so we'll talk about, somebody remind me to talk about testing next time. But to finish, how can we actually restrict these things to only work for random walkers, right? Because really this function walk, well, it really only works for random walkers, let's be honest, right? For anything that walks. So how do I define that? So that's what these abstract types are for. So really what I want to say is, well, a discrete walker is a type of walker, right? That's what I want to say. I want to be able to tell Julia that. A discrete walker is a type of, or kind of, walker, right? So I need a way of saying what a walker is. And so that's what an abstract type is. So let's call it an abstract type, sort of random walker, end. That's all we do. Oops. Sorry, no space. Random walker, end. So what does that do? That defined a name called random walker, which is a type. If I try and say what methods are available to make that type, to make an object of that type, the answer is none, because you cannot make objects of an abstract type. The only thing that an abstract type does is exist to group other types underneath it. So let's redefine our discrete and continuous walker. So this is, well, we'll lose the my. So I'm gonna, because I can't redefine them with the same name. So let's just say mutable struct discrete walker is a subtype of random walker. So I put this less than colon operator. That means this is a subtype of random walker. That means just a discrete walker is like, you know, a specialized type of random walker, and that has an X, which is an N64. And then similarly, I'll define a mutable struct. I'll just copy that code and paste it. Oh, come on. Continuous walker, which is also a subtype of random walker. That is the point. So random, you know, both of these, and that has a Y, which is an int64. And then I would have to go through and define, well, and then what can I define? Yeah. So I need to define, again, pos of X, which is pos of W, which is a discrete random walker, is, you know, W.X. Pos of W, which is a continuous random walker, is W.Y. And then I would define set pos, etc. And I would have to define the jump functions. I'd have to go through and redefine all those functions. And what is the point? The point is that now to restrict those functions like walk. So let's just copy the code again. So now I want to restrict this to work on just to accept a random walker as the first argument. Well, now I can. Now I can just say, this will only accept an object, which is, in quotes, of type random walker. What does that actually mean? It means of any type, which is a subtype of random walker, because random walker is an abstract type. Right, so now I can, so once I've defined all of these jump functions and everything for these two types, then I can define this, and now I can own, for this version of the function, will only accept an object of W, which is of a subtype of random walker. So if I actually create one of these things, so I create a discrete walker at position 10, I can say, is W a discrete walker? Of course it is, because I created it as being an object of that type. But now I can ask, is W a random walker, which is this abstract type? And the answer is also it is. Right? That's the point. So as long as, so I have what's basically a type hierarchy. I have these types being subtypes of another type, and I can do that in different layers, different nested levels. And so what that means is, so when basically what Julia's doing is checking when I'm calling an object, which version of the function will, will accept an object of that type. And in this case, it will accept any object that's a subtype of random walker. And so in that way, I can restrict to, these functions to just working on special categories of objects. Okay, so I know it was pretty heavy and technical, this lecture, but hopefully it cleared up some points about how to define types in Julia, why we should do that, what the syntax is, and what the sort of way of thinking about these things is, and this idea of defining these small functions all the time, building up on top to get to a result where we can actually say, oh yeah, I know what it means for an object which is some kind of random walker. Now I can define how to do a random walk for any object of that type, and it is the same piece of code for all of those objects. And what is going to change is just what's inside this jump bang function. Right? So I think that is it's pretty nice that you can package everything up in these small bite-sized pieces, and build it up and understand what's going on and make sure everything works at each step, and build up some useful functionality like that. Okay, that's the end of the class. So thanks for your attention and hope it was useful. So you're going to use these types in problem set 3. You don't need to do these abstract types yet. That'll be in the next problem set, but you do need to know how to access some data inside a type, and then how to change that data. And then you're going to need to make vectors of objects of that type as well. So let's just see how to do, well, okay, we'll see that next time, I guess. Yeah. So yeah, well, I'll just say it. So I can, make a vector with sort of a random walker, well, a discrete walker at position 1 and a discrete walker at position 2, just like that, right? And I get a vector. It knows that it's a vector and it has to contain objects of type discrete walker, and there they are. So it's just like creating any other vector in Julia. You'll need that. Okay, thanks. So no lecture on Monday. See you next Wednesday. Thanks, bye.